All right. Well, hey, welcome to March. Yeah, we're already here in March. This is the last month of the quarter. We are cruising right along. In fact, if you want to just think about this real quick, the final exam is 3 weeks from today. Holy cow, time has been flying. Anyway, so we're moving right along. My plan today, after giving you guys a chance to ask about homework and talk about that a little bit, we're going to move into chapter 11. I think we're going into. We're going to talk about this thing called the chi-squared distribution and some of the stuff it's used for. So we'll talk about that for a bit, and then we'll spend some time later today talking about the exam that's coming up on Thursday, because I want you to be prepared for the topics that are going to be on it, what kind of things I'm going to expect you to need to know. And this way you can ask some questions if there are some things that are still a little foggy. All right, so that's my plan for today. So let me go ahead and turn it over to you guys. What would you like to see from homeworks? Because I see a couple of you've already started chatting about it. What do we want to talk about?
Mine is number 1 and 3 from the latest assignment, which was the proportions.
Okay. Got that on the list. Thank you, Bruno. Any others?
Is there any way we can look at question 2 from the hypothesis testing for matched pair samples?
Sure.
Okay, thank you.
So number 2, matched pairs. And Allie says number 1 from the first section. I think that's also matched pairs, right? Question 2 will suffice. Okay. Seeing they're pretty much the same kind of question. All right. Yeah, and Allie, I don't know if you got my response to your message, because I went and looked at the ones that you got wrong to see what was going on, and no, you did not get it. Okay. Well, I responded to it earlier today, so maybe check your Canvas. But anyway, at least going over it here should help you see. All right, well, let me go then, and we'll go take a look at that guy. Let's jump over here. Okay, so let's start with the matched pairs. And we'll look at number 2. So that's the one that Ashton wanted to see in particular. But and Allie said that should be good enough. All right, so is the average time to complete an obstacle course longer when a patch is placed over the right eye than when a patch is placed over the left eye? All right, so we're gonna make you be a pirate and run the obstacle course. And then we're gonna switch eyes and make you do it again. But we got 13 randomly selected volunteers first completed the obstacle course with a patch over one eye, and then completed an equally difficult obstacle course with a patch over the other eye. The completion times are shown below. Left means the patch was placed over the left eye, and right means patch was placed over the right eye. Okay, so there's our data. So we had some people ran the obstacle courses, and here's the information. So person number 1 took 41 minutes. We'll go with the minutes, 41 minutes when they were covered with the right eye, and 35 at the left, and so on down. All right, so it says assume a normal distribution, which is pretty standard. What can be concluded at the alpha equals 0.05 level of significance? I think it's funny they always say that twice. All right, so for this study, we should use, all right, so what are we going to do here? Are we going to do a t-test for the population mean, a z-test for population mean, a z-test for the difference between two population means, t-test for the difference between two independent population means, or t-test for the difference between two dependent population means? Whew. So which of those are we doing here? All right, so Bruno just put in the chat box there the t-test for dependent population means, and Ali put in t-test for pop. Okay, so let's think about this. So first of all, we know we're not doing a proportion. You can definitely rule that out because we're not looking at percentages, right? This isn't what percentage of people ran faster, what percentage of people covered their right eye, like nothing like, there's no percentages. So it's not a proportion. So we're not doing the z-test for population proportion or the z-test for the difference between two population proportions. Okay, so then let's think about this. We can rule out the t-test for a population mean because we don't have a population and we're not looking at the average for the population. We're actually looking at the difference in these two. So it's definitely going to be one of these, a difference between the means. But is it independent or dependent? And it is dependent because these are the same person, right? Like maybe this first one was Bruno, right? And the second one was Ali, and the third one was Ashton, and this was me, and you know, like, okay, so we just go down the list. So like if we were to look at this, if these are both Bruno, they are definitely dependent because he is doing both of them and there's some commonality, right? So they're definitely dependent. So we're going to do t-test for the difference between two dependent population means. All right, so the null and alternate hypotheses will be, all right. So we're looking at a difference, the mu of the difference. Since this is a null hypothesis, it's going to be equal to, and it's going to equal 0. Or alternatively, we could write, if we're going to look at, say, right is 1 and left is 2, we can say that those two means are equal, but that we really want to reserve for if we're doing independent population means. So we're going to go with that their difference is actually equal to 0. Okay, so the alternative hypothesis is still going to have difference in 0. But again, remember what we're looking for is is it longer when the patch is over the right eye than when the left eye? And so if we do say right minus left, I'm going to do mine as greater than 0. All right, now this is one thing I am going to tell you that I'm not super thrilled with this homework, the way that this homework is designed, is depending on how we do the differences, we could be looking at greater than 0 or less than 0. So, you know, when they tell us to put it in a specific way, we might get different responses. So we'll just sort of have to see how this plays out. All right, but I'm going to do it this way, that I'm looking for right minus left. That's how I'm going to do this. I'm going to do right minus left, and I'm going to see, is that greater than 0? Right? Does that mean that it takes longer when it's over the right eye versus the left eye? All right. So now we get to go have some fun and create or do our calculations here. So let me just really quickly write down the numbers here so that when I switch over to the whiteboard and the calculator, we've got the values. So 35, 44, 42, 40, 38, 43, 42, 44. Uh-oh. Okay, think I've got them all. I hope I've got them all. We're going to find out real fast. Okay, so what we need to do is calculate the difference in their means. Right? So here's what we had. So right and left. And here were your values. So 41, 43, 42, 45, 40, 48, 43, and 48. Okay, so those were the times with the right eye patch. And the left eye patch were 35, 44, 42, 40, 38, 43, 42, 44. Okay, so I'm going to calculate right minus left. In fact, I'll just go ahead and do another row here. But I'm going to calculate the difference in these two, right? Because again, that's what we're interested in, is what is the difference between these two values. So right minus left, that was a 6-minute increase. The second one, -1, 0, 5, 2, 5, 1. That was a 48, so that's 4. Okay, so I'm just calculating the difference in these. So again, what I want to know is this greater than 0? So these differences, these are the numbers that I'm going to put into my calculator. I'm going to put those in when I do my t-test. All right, so we okay with that so far? All right, so let's go to the calculator. So I'm going to go to stat. We're going to edit because we're going to put these numbers in somewhere. Yeah, let's go ahead and put them in here in L2. So I'll go ahead and clear that out. All right, so the numbers I'm going to put in here were those differences that we saw along the way. So again, come back. Remember this right here? The 6, -1, 0, 5, 2, 5, 1, 4. Those are the numbers that are going to go into our calculator here. All right, so we had 6, -1, so -1, 0, 5, 2, 5, 1, and 4. I still want to make sure I got those numbers right. Let's see. 6, -1, 0, 5, 2, 5, 1, 4. Okay, so we've got our numbers. They're in L2. So now let's go to stat. We're going to do a test. And we're doing a t-test. We are using data to do this t-test. So I'll arrow over and do data. All right. So the mean that we're testing against is 0. Every time you're doing one of these compares, you're going to go with the value of 0 that you're comparing against, right? We want to know, is this positive or negative? Right? So we're going greater than 0. Our list is L2. Whoops, wrong arrow. So L2, we'll get that second L2, frequency 1. Okay, but we were looking for, is this difference greater than 0? Right? The fact I was doing right minus left is telling me I want to see, are these things bigger than 0? So we'll go down here and we'll calculate. It thinks for a minute. And so there we go. We get a T of 2.986 if we round it, and a P of 0.01017. I don't know how many decimal places it's going to tell us to go, so we'll come back to that in a second. All right, so let's go back to the homework question. Okay, so our test statistic was a T equals, and it says to go to 3 decimal places. So we had 2.986 to 3 decimal places. And then our p-value was 0.01017. So I guess if I round that to 4 decimal places, 0.0102. Okay, so our p-value is less than alpha, less than or equal to alpha, right? Alpha was, I forget, what were we, 10%? What does this say? Oh, there it is. Alpha 0.05. Okay, so we got alpha is definitely bigger than our p. So what do we do if our p-value is less than alpha? Every hypothesis test. What do you do if your p is less than alpha? Good, Ashton. We're going to reject the null hypothesis. All right, because this means, remember what this p is. This is the probability that these results would happen if our null hypothesis was true. So this is saying there's only about a 1% chance that we would get a set of data like this if our null hypothesis were true. So that means most likely the null hypothesis is not true. So we're going to reject it. Okay, so we're going to reject the null hypothesis, which makes us think that there is a difference. And it definitely appears that it takes longer if you're covered, if your right eye is covered. Okay, so let's see which of these statements most sounds like that. Results are statistically significant, so there's sufficient evidence to conclude the population mean time to complete with over the right eye is greater than that for the left eye. Well, I think that's the one we're going to pick. Right? We're not going to say that it's statistically insignificant because we definitely got a p-value less than it. All right. So the results are statistically significant. So there's sufficient evidence to conclude that the 8 volunteers that completed the course slower on average with the patch over the right eye compared to the left eye. Hold on a second. That one also sounds like what we want. So maybe we should read these again a little more closely. So this one says the results statistically significant. So there's sufficient evidence to conclude that the population mean time to complete the obstacle course with the patch over the right eye is greater than the population mean time to complete the obstacle course over the left eye. This one's saying the A volunteers completed the course slower on average with the patch over the right eye compared to the left eye. That's actually the one I want. Because the first one's saying that the average time with the right eye is more than the average time for the left eye, which is not what we tested. We didn't look at all at the average of the right versus the left. But this one definitely says that they were slower on average with the right eye than the left eye. So I think that's the one we want. All right, so let's submit our question because I'm actually really curious. I'm mostly curious about this H1. I mean, I guess H1 says I'm wrong there. Oh, no. It's that one you didn't like? Oh, I see what the problem is. Hold on a second. Let me get my correctness. Let me explain why. Okay, so here was the issue why this one was wrong when I chose it this way. Because we were just looking at the 8 volunteers. Remember what we're testing? We're testing we're using the sample to test the population. And so our conclusion from a test is always about the population. So it's that word right there, the population. That's why that's the one I wanted. All right, so did that help with this one? I hope. And I also want to follow up with Allie. Is this good enough? Because you said number 1, but number 2 would be sufficient. Is this good enough for your questions? Yeah. And then, yes, Allie, it should have been a Canvas message that I sent you. We'll figure out what's going on with that later. All right. So there was that one from matched pairs. But there were also the questions from the proportions set. So let's go take a look at that one. All right, so hypothesis test for a difference between 2 population proportions, and numbers 1 and 3. I don't know if we'll do both of them, but we'll at least talk about both of them. How about that? All right, so here's number 1. So is the proportion of wildfires caused by humans in the South higher than the proportion of wildfires caused by humans in the West? Okay. So 368 of the 533 randomly selected wildfires looked at in the South were caused by humans, while 305 of the 506 were in the West were caused by humans. What can be concluded at the alpha equals 0.1 level of significance? All right, so first, for this study, we should use, well, this time we're looking at proportions. So you can rule out, oh, the video didn't work. Okay, well, we'll walk through it. So we can rule out population means, right? So the top 3 are gone. So then is it a z-test for a population proportion or a z-test for the difference between 2 population proportions? And it's the z-test for the difference between, because we're comparing 2 different population proportions. Okay, so the null hypothesis is going to be that proportion for 1 is equal to the proportion for 2. So I know I'm using p's instead of mu's because these are proportions. And I want this equal because the null hypothesis is always equals. All right, so then these are still going to be P1 and P2. But now the question is, do we use less than, not equal, or greater than? We're not going to use equal. Well, let's look at what they're asking. Okay, so I like greater as well, because remember what they're asking says, is the proportion in the south higher than the proportion in the west? So if P1 is the proportion in the south and P2 is the proportion in the west, then we're looking for P1 greater than P2. Okay, so the test statistic is going to be a Z. But let me write down these numbers so that we can go plug them into the calculator and see what happens. All right, so I'm going to switch to the calculator. All right, so this time, again, we're going to go to test. So we'll go stat. We're going to arrow over to test. But this time, we're going to do if we arrow down here, a 2-prop Z test. So remember that the prop stands for proportion. So we're doing a 2 sample, so 2 proportion Z test, so 2-prop Z. Okay, so let's start with our first set of data. We had 368 out of 533 fires in the south. In the west, we had 305 out of 506. And again, we want P1 to be greater than P2. That's what we're looking for, right? Is the proportion higher in the south than the west? All right, so let's hit enter. And we get some numbers. So our Z is 2.9568 and change. Our P is 0.001554 and change. And then we've got P hat and P2 hat and all that good stuff. So again, let me just remind you what all these different things are. So the Z is our test statistic. And then the P is the P value that goes with it. This one, P1 hat, that's actually the proportion of fires that started in the south that were caused by humans. P2 hat, this is the west, the western ones, so 0.602. And then this one that's just plain P hat, this is pooled. Hopefully you remember pooled means we're putting them together, so we get a pooled proportion. And that pooled proportion, the 0.647738, that would be if you combined both the west and the south's numbers and did the division. Okay, so there are all those numbers. So let's go back to the homework here. Okay, so we just got a Z score, and that Z was 2.957. If we go to 3 decimal places, the corresponding p-value was 0.0016. If we go to 4 decimal places, we see that that p-value is less than or equal to alpha. And so again, we're going to do the exact same thing we did on the last one, which is reject the null hypothesis, right? This is a very rare occurrence if the null hypothesis is true. If these proportions were actually equal to each other, we would get the kind of information we just found about 1 out of every 900 sometimes. So that's very rare. I mean, it's less than 1% even. So we're going to go ahead and reject the null hypothesis. So we do have statistically significant results. And what we know, we're going to go to this one right here, which says results are statistically significant. So there's sufficient evidence to conclude that the population proportion of wildfires caused by humans in the South is higher than that in the West. And we're going to go to that one instead of the first one, because the first one's about the sample itself. But remember, the hypothesis test is testing about the population. All right, so I think we should be good. Let's go ahead and submit our question. Yay, 3 out of 3. So let's just take a look at 3, because 3 is kind of similar. Actually, I'm sorry, before I jump away from there, was everybody good with 1? Did that make sense? Everybody see how to go about this? Yeah. Okay, so let's go look at number 3. So medical researcher is comparing 2 treatments for lowering cholesterol. One is diet and the other is meds. So the researcher wants to see if patients who receive the recommendation to change their diet have equal success lowering cholesterol compared to the prescriptions. All right, so a random sample of some patients who received the recommendation to change their diet and others that were prescribed medications were taken. The results, how many did or did not lower their cholesterol, are shown below. Okay, so the people that just changed their diet, 385 of them dropped their cholesterol, 127 did not, right? The ones that took the medication, 544 of them dropped their cholesterol numbers and 227 did not. So that's how to read that. All right, so for this study, what should we use? All right, so what do you think? Let's just start here. Are we doing something with means or proportions? With this question, what are we actually testing? Means or proportions? So Bruno just said, would it be proportions with a question mark? And the answer to that is, yep, absolutely. We're looking to see what percentage of people were able to drop their cholesterol. We're not looking at what's the average amount of drop in cholesterol, right? If it was, okay, well, we're going to go down the list again and we're going to see, you know, who did what. Okay, so Carson's cholesterol went down 12, right? And then Allie's went up 3, and Tassel's went up 4, and mine went down 6. Okay, so if we were doing that, then we'd be looking at means, but this one's definitely proportions. And so if it's proportions, again, there's 2 that we can be doing. Are we looking at the difference between 2 population proportions or a population proportion? Well, it's 2, right? There are 2 populations we're looking at. We're looking at those that change their diet and those that are taking these medications. All right, so the null hypothesis then is going to be proportion equals proportion. Proportion 1 equals proportion 2. All right, that it's the same whether you take these medications or change your diet, same proportion, have successful loss of or lowering of cholesterol. Okay, so what about the null hypothesis? Again, it's P1 and P2, but what's going to go in here? Greater than, not equal to, or less than? And I'll help you out because we need to read it. So let me get up to the top there so you can read the whole thing. So is it greater than, not equal to, or less than?
Not equal to.
It is not equal to. And how do you know that? I think that was Carson that just chatted.
It's saying the researcher wants to see if the patient who will receive the recommendation will have equal success in lowering the cholesterol.
Exactly, right? So if you look at this, it says, did they have equal success? Not greater success, worse success, different, right? So in this case, the claim that we're testing is actually the null hypothesis, right? But we're trying to see if they're equal. So it's, are they the same or are they different? That's what's being asked here. All right, so the question then is, what does the test tell us? All right, now this one, we're gonna have to be a little more creative when it comes to entering the information into our calculator. We're still gonna use the same test. This is still gonna be a 2-prop, right? So it's 2 population proportions, so it's a 2-prop Z. And you may remember what we had to put in there were the X's and the N's. And so in there it was, X was how many actually did what we wanted. And then the N was total. And here we're not given totals. We're given the 2 X's, right? That the 385, that's X1. 544, that's the X2. But for the N's, we actually need to add up these columns. So like this one, you add those up, you get 512. So 385 out of 512 were successful at lowering cholesterol just by using change in diet. Okay, same thing over here. We have to add these up, and that gives us what, 771, I think. And so 544 out of the 771 were successful at lowering their cholesterol by taking the medications. All right, so this one just adds a little bit of a challenge because they don't specifically tell us what the N's are, okay? But let's go ahead and go over here. We're gonna do test, 2-prop Z is 6. All right, so I wrote down these numbers. So the first one, it was 385 were successful when they changed their diet. And that was out of 512. All right, so then the ones that would use medication, 544 were successful out of 771 total. And then this time we want not equal to proportions, right? We just want to see different or not. All right, so assuming I did my arithmetic right, we'll go ahead and hit enter. All right, so for this one, we get a Z of 1.8199 and a P of 0.068766. All right. And again, notice that we have the same numbers popping up again. So P1, that's the proportion from just changing your diet. 75% of them were successful in lowering their cholesterol. P2, that was for the meds. So 70-ish% of those that just took medication. And then the pooled is the 72.4%. All right, so we'll go back to our homework here. So our test statistic was a Z score. And the Z here was 1 point, how many decimal spots? 3, 1.820. And I think this came up once before, but I want to remind you that, yeah, that 0 does need to be there so that we know that it's been rounded at the 3rd decimal place. If you just dropped it, if you wrote 1.82, that only tells me that you rounded it to the 2nd decimal place, not the 3rd one. So we always want to fill those in if necessary to show where we rounded. The p-value was 0.0 0.06, how many spots? 4 spots. 0.688. All right, so that's the information we got from the calculator. So now we answer this. So the p-value is, compared to alpha, we're now bigger than alpha. So what do we do now? When it was less than alpha, we rejected the null hypothesis. If it's bigger than alpha, what do you do?
Fail to reject.
Good. Fail to reject. It's really tempting to say, okay, now we're going to accept the null hypothesis. But no, this time we're going to fail to reject. All right. So then what's our final conclusion? Well, it's statistically insignificant. Right? So it's going to be one of these, but let's read which one is the wording of fail to reject versus accept. So the results are statistically insignificant. So we can conclude that the success rate for all patients who receive the recommendation to change their diet is equal to the success rate for all patients who are prescribed meds. Or conclude that the population of all patients who receive the recommendation to change their diet is not equally likely to lower their cholesterol as the population of patients who are prescribed meds. So which one do you like? The first one or the second one? Now I feel like I'm a optometrist. Which is better, number one, number two? Number one, number two. And
Number two.
For those of you who've never been to an eye doctor, you have no clue what I'm talking about. All right, so I don't know who that was, just said number two. I talked over you. I'm sorry. Was that you, Allie?
Yeah, that was me.
Yeah. Okay. So when you say number two, you mean this one down here?
Yeah.
Okay. So what do the rest of you guys think? So there's insufficient evidence to conclude that the population who change their diet is not equally likely to lower, right? Versus, think about what this one is saying. This one says, we can conclude the success rate for all patients who change their diet is equal to those who are prescribed meds. That would be accepting the null hypothesis, right? That's saying, nope, those are the same. But that's not what we do, right? This is the, well, we don't have enough information to say that they're different. So that is definitely the one we want to go with. All right, so then let's interpret the p-value in the context of the study. Okay. So think about what that p was, 0.0688. So there's a 6.88% chance that the difference in the success rate for all patients who receive the change of diet and all patients who are prescribed meds is at least 4.6%. There's a 6.88% chance of a type 1 error. If the success rate for the sample of patients who receive the recommendation to change their diet is the same as the success rate for the sample of patients who are prescribed meds, and if another 512 patients were given the recommendation to change their diet and 771 patients are prescribed meds, then there'd be a 6.88% chance of concluding that the difference in their success rate who receive the recommendation to change their diet is at least 4.6%. Versus this other really long one. Hold on, let's see. So same success rate, are prescribed meds, another 512, so there would be a 6.88% chance that the percent of surveyed diet changes who lowered their cholesterol would differ at least 4.6% compared to the percent of the surveyed med takers who lowered their cholesterol. Whew. All right, so which of those do we want? 1, 2, 3, or 4? This is a lot more challenging now, right? Any clues? So Bruno would say 3. Since it was his question, we'll go ahead and mark 3. What do the rest of you guys think? All right, well, we'll leave it at 3. We'll see if we're right or not. All right, so then interpret, I didn't mean to click there. Interpret the level of significance in the context of the study. Okay, blah, 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 blah. There'd be a 5% chance that we would end up falsely concluding that the proportion of the 512 who changed their diet, lowered their cholesterol, is different from the proportion that lowered their cholesterol. Okay, or 5% chance that we would end up falsely concluding that the success rate for the population of patients who receive the recommendation to change their diet is different from that who are prescribed meds. Okay, so I agree. It's definitely going to be one or of those. Let's think about alpha. What kind of error is alpha the probability of having? Was that the type 1 or the type 2? So Bruno just put in the chat box type 2 with the question mark. You're close. That was a joke. There's only 2 options and you're not right. It's obviously the other one. It's type 1. So alpha is our probability of making a type 1 error. Okay, so there's a 5% chance, since alpha is 0.05, there's a 5% chance of a type 1 error. So which one is a type 1 error? We can put that in the language when I kind of taught it to you. We were going with the null hypothesis is the defendant is guilty. So a type 1 error was you let the guilty person go free. Meaning we fail to reject the null hypothesis when we should have rejected it. So the null hypothesis here would say that the proportions are the same. Right? And so the null hypothesis is saying, oh, we rejected the null hypothesis when we shouldn't have. That's a type 1 error. So this would have been, we would have said, no, we think there's a difference when there actually isn't. So which of these wordings is basically saying that? And I think that's the first one. All right, we're going to falsely conclude that the proportion is different when it actually isn't different. Okay, so let's submit our question. Uh-oh, we got something wrong. Oh, we got 2 things wrong. All right, so for G, this was the one when Bruno said it's A3. It's actually going to be number 4. And the reason that this one is number 4 instead of number 3, if you look at this again, it's sort of the same setup. If the success rates are the same and we sample another 512 and 771, right? They're all the same. But this one said there would be a 6.88% chance of concluding that the difference in the success rate is at least 4.6. And then this one says there would be a 6.88% chance that the percent of the surveyed would differ by at least 4.6. So it's slightly different wording. But this one is talking about the percent chance that the difference in the success rate as opposed to the difference in the percents of the surveyed. So that's why that one is. And then this guy, falsely concluding the success rate for the population is different. %5 chance. End up falsely concluding that the okay, because this one was concluding the proportion is the same as opposed to the success rate. That's why that one's wrong. We should be good now. There we go. All right, so the wording on this can get really kind of confusing. I'm not a huge fan of how they write their things up, but what's important to get from this in terms of P and alpha and all that, alpha is the probability of making a type 1 error. Okay, so remember that. And what we're trying to do is we're trying to minimize a type 1 error. So that's why when we judge ourselves against alpha, we're still saying, well, we might be making a type 1 error, but we're going to try to make that small. Okay. And then P, that's the probability that this result would happen if the null hypothesis were true. I like to think about P that way. I think it makes a lot more sense than kind of how they're talking about it. They're kind of two sides of the same coin. But I like to think of it as that's the probability that this would have occurred if the null hypothesis is true. Because I think that really helps you think about, because think about what we're trying to do. We're trying to either reject or fail to reject null hypothesis. So it's all about the null hypothesis. So if that p-value is really small, that tells you that this is very unlikely to have happened if the null hypothesis is true. Which means I don't think the null hypothesis is true. As opposed to if p is really big, that's not uncommon. So I'm going to say, well, I don't really have evidence to say that the null hypothesis is wrong because this isn't a really rare result. Now, if you start getting big p-values like 0.9, 0.95, you start going from the realm of failing to reject to I'm going to start accepting this. Where you start going, okay, there was only a 5% chance that this wouldn't have happened. Okay, then most likely that's true. But again, we only ever reject or fail to reject the null hypothesis. Whew. All right. Anyway, hopefully that helps a little bit in terms of doing the hypothesis testing. It all just comes down to the P, right? Put it into your calculator, get the P, and compare that P to the alpha. That tells you exactly what to do. All right, so any other questions on the homework at this point? All right, you're welcome, Bruno. See you later. Okay, well then let's move on to another distribution. Let's talk a little bit about this new guy. But I need to take a real quick break. I need to get something to drink. My throat's getting a little dry. I just realized I've been talking for like an hour and 15 minutes nonstop. So let's just take a real short one. Let's come back my clock says 4:44, so let's come back at 4:50. We'll come in 6 minutes. So you'll know I'm back when I show up on the whiteboard screen. All right. So I'm going to go ahead and turn both of mine off, but when I come back in front of the whiteboard, I'll be ready to go. So see you in like 5 or 6 minutes. All right. So I'm back. Give you guys a second to sort of get back into it yourself. But today what I'm going to do is I'm going to show you another distribution. This is one we call the chi-square distribution. And we'll actually look at one of the things that we can do with it. There are a bunch that we can, a bunch of tests we do with the chi-square. But we'll just talk about one of them today. We're not going to get too crazy since we've got an exam coming up here anyway. So let's start with that. So the chi-square distribution. It's another one that was kind of made up to use to do tests with, kind of like the student T distribution. But this one is called the chi-squared distribution. So chi is a Greek letter. It looks like an X. I'm going to make it nice and curvy, make sure that y'all can tell that it's not a regular X like we use when we're talking about the variable. But the chi-square is written like this. All right, so again, this is the Greek letter chi. It's their third to last letter in the Greek alphabet. Anyway, so that guy's chi. So this is a chi-squared distribution. And chi-squared, it's a lot like the T distribution in that its shape depends upon the degrees of freedom. Okay, so anytime you have a chi-squared distribution, you're going to have down below little subscript like we've done before, we're writing down here, where there's going to be a number for your degree of freedom. Okay. Now we'll talk about what how we determine what the degree of freedom is. It depends what test we're doing. But the degree of freedom changes the shape of this. Now, here are some things about the chi-square distribution that are kind of important. Okay, so like I just said, like the t-test, it depends on the degree of freedom. So we always have to state what the degree of freedom is if we're going to use the chi-square distribution, because it really changes the shape a lot, a lot, a lot, a lot. Turns out that if the degree of freedom is greater than 90, where 90, just smile and nod, okay, the 90. If degree of freedom is greater than 90, then it's a good approximation for normal. Now, what's nice about this is that if we're in a situation where we've got such a big degree of freedom, we can just jump straight to a normal test. All right. But for the things we're going to do, this isn't all that common. We're not going to have degrees of freedom this large. Most of the things we do are going to have degrees of freedom on the order of like 4, 5, 6, 2, right? So we're going to be far away from that. But as the degrees of freedom get bigger, it gets more normal. The other thing that's kind of interesting about this one is that these are not symmetric. And in fact, it's skewed right. Now, I don't know if you remember when we talked about skewed way back when. Oh my goodness. I don't remember when it was when we first started talking about distribution functions and them being skewed. That was way back like chapter 4 or 5 or something like that. But what this means, the skewed right, it means that the peak in the distribution is shifted left. And what I mean by that, let me draw you a graph of one of these. All right, so here's a representative of the chi-square distribution. Again, depending on what your degree of freedom is, you'll get a different shape. But it would look something like this, for example. So notice that this isn't normal. Like a normal distribution would look more like, let me do black. A normal distribution would look something more like that, right? Where it's nice and evenly symmetric. That's a better one. All right, so there's our classic bell curve. But you'll see that this red one isn't symmetric. It doesn't look the same on either side of the peak. And the peak has been pushed a little bit to the left. So this is one that's what we consider called skewed right. Anyway, so it's definitely not symmetric. And it turns out that the mean is just a little bit to the right of the peak. So if you think about that high spot on the red graph, because the red graph is actually our chi-square distribution. If this is where the maximum of the peak is, where this green line is, the mean is always found a little bit to the right. And that's what skewed right means. Because like with a normal distribution, the mean is at the peak. Skewed right means the mean has been pushed to the right a little bit. All right, so there's just some information about the chi-square distribution, just so you know about it. But let's talk about why we actually care about it. Because I know not a single one of you in here, this is nothing personal, I know the students, not a single one of you cares about any of this at all. You want to know, okay, what are we going to do with it? How's it going to be used? If I'm not going to use it, I don't care. So let me show you some of the things that we use the chi-square distribution for. So you think about like the normal distribution and the student t distribution, you've started to see a lot of use for that, right? All the hypothesis testing and all that kind of stuff. Well, the chi-squared is also used for hypothesis testing. And it's used really for three main things. At least these are the three we're going to talk about. Okay, the first one is we use this for what's called goodness of fit. And goodness of fit is pretty much what it sounds like. Right? What this is saying is we're going to test how good does data match an expected distribution. So this would be one of those things where we go in thinking, all right, maybe we're told by the CDC that 15% of people under the age of 20 who contract COVID are heal within a week. 38% of them heal within 7 to 10 days, and so on. So we got kind of like a distribution for how long it takes people to heal. So we go, okay, well, let's go actually find people under 20. Let's go sample them, and we'll get those numbers. And goodness of fit will tell us how good does that data fit the distribution? Are we getting what we expect? Okay, so that's one of the things that we'll do with chi-square. And we'll do that today. It's actually a pretty easy thing to do. Excuse me. All right, another thing that we can use it for is a test for independence. That too is exactly what it sounds like. We're going to use this to determine are two variables independent. Now, we've talked about way back when we talked about probabilities. Remember, what things were independent if the probability of one given the other is the same as if that condition wasn't there at all. But sometimes we don't have that information. We don't actually know those probabilities, so we can't calculate it. But the chi-square distribution will let us look at the different groups and go, oh, are they actually independent or not? Right? Like maybe we want to know, are statistics exam scores, our average statistics exam score, independent of what college you go to? Is there a difference between LTCC and UNR and Davis? Or do students that take them at any of the places get similar success rates? Right? That's where we would use like test for independence. Is your success dependent upon where you go? All right, so that's the second one. And then the third one is a test for single variance. So we call it a test of single variance. And again, it's exactly what it sounds like. Well, what this is going to do is it tests the variability of one sample. So an example of this would be, well, maybe we're going to look at cans of root beer. And we're going to see how much root beer is actually in each can. Now, we know when you look at the can, it tells you how much is in there, right? So it's 12 ounces, 353 milliliters. But we know that we're not always going to get 12 ounces, right? Maybe we get 12.01, maybe we get 11.94, and so on. So if we wanted to do a study and see how good is this place at being consistent with their quantity of root beer put into their can, that's where we would use a test of single variance. All right, so these are the three big things that we use the chi-square distribution for. And today, we're just going to talk about number one. We're going to look at goodness of fit. All right, so here's how this is going to play out. Let me actually give you an example. We're going to start with an example just so that you can kind of sort of see the sort of situation where this is going to come up and what we're going to want to do. All right, so let's just say we think that there is no preference in the flavor of Lifesaver candy. All right, so you know Lifesavers, right? The little around fruit flavored ones. And if you go to the original pack, just the fruit flavored pack, I think it has 5 different fruit flavors. I don't remember what they all are, so I'm going to make them up. But maybe we think that there isn't a preference. That if we were to go and ask, 100 people, which of the 5 flavors of Lifesaver is your favorite? that we're going to get an even distribution. But it's just as likely that you say cherry as you would say orange. Okay, so maybe that's what we think, right? And let's get here that there are 5 of them, right? There are 5 flavors. So we go ask 100 people. Okay? So we go actually ask 100 people, what's your favorite flavor? And this is what we find. So the flavors are cherry, orange, lemon, lime, and pineapple. I think those are the 5. All right, so we ask those 100 people, and this is what we find for their numbers. 32 of them say cherry is their favorite. 28 say that their favorite is orange. 16 of them like the lemon. 14 like the lime. And 10 of them like the pineapple. All right, so here's the question. Is our assumption correct? Is it actually that there isn't a preference for flavor? Now, if you just looked at these numbers, I think you'd probably, like if I just said, what do you think right now? Are there some flavors that people like better than others? Throw in the chat box, yes or no. Give me a thumbs up for yes. Give me a party symbol for no. Okay, so most of you are saying, yeah, it looks like there's a difference, right? I mean, come on, let's look at pineapple versus cherry. There's pretty huge difference between those. So it seems like our thought is probably incorrect. But you know us, like statsy kind of people. We don't like words like we think. We want evidence. We want to be able to say, you know what? Yeah, these are the numbers. This is what it says. All right, so we're going to do a hypothesis test. Here are what the hypotheses are. The null hypothesis. So this one, I'm going to write it in words. And when you do goodness of fit, it usually is in words, but the null hypothesis is going to be that there is no preference in the flavors. Okay, so overall, there is no preference in what flavor the candy is. The alternate hypothesis then would be there is a preference. Or an alternate way of thinking about these hypotheses, not an alternate hypothesis, but an alternate way of thinking about it, is the sample follows a uniform distribution. Or let's not go to the sample, the population follows a uniform distribution. Right? If we're saying there's no preference, if we were just to look at the distribution of responses to which flavor is your favorite, it would be the same every time. Okay, so our null hypothesis is the population follows a uniform distribution. So the alternative hypothesis would be It does not. Over here doesn't follow. And I'm just going to write uniform because I'm running out of space. Right. But. All right, so this is our guess. We're asserting the null hypothesis, but we want to test it. So we need to have an alternate, a way to test this hypothesis. All right, so kind of cool with the idea. I know that right now you're like, I have no idea what chi-squares mean anything, but we get the feel for what it means to do goodness of fit. We're trying to look at our data and say, hey, is it following a distribution that we expect, right? Like, think about this. If this is our observed, let me actually, I'll write this as, this is our observed column. What should we have expected? I'll make a little column here that says expected. What kind of values should we have expected if it were equally distributed? So if I go and I ask 100 people, how many should have said cherry was their favorite? Okay, thanks, Willie. Yeah, it's 20 in each one of them, right? If they truly were all equally likely, I should expect, I ask 100 people, 20 of them say cherry, 20 of them say orange, 20 say lemon, 20 say lime, 20 say pineapple. Right. So this is what we're really doing. When we say goodness of fit, we're saying how good do the observed numbers fit our expected number? All right. So to use the chi-square distribution, we're gonna have to come up with a test value and then a way of testing that test value. And so, all right, well, here's how this is going to play out. So first of all, we have to determine the degrees of freedom. Well, the degrees of freedom it's always going to be the number of categories minus 1. Now, this is a little bit different than with the t-test. I mean, you're used to subtracting 1 for the t-test, but do you remember what you subtracted 1 from for the t-test? Like, how did you figure out degrees of freedom for a t-test? What was it that you took 1 from? All right, so Willie, you put P. What do you mean by P? Because that's not the letter that I'm used to. It might mean the same thing. Oh, you just gave me a never mind. I hate that. I mean, you start questioning yourself and you're like, I don't know. Maybe you were thinking it was like the population or something like that. That we subtracted from n from our sample size. Just a real quick refresher. So for the t distribution, degree of freedom was always n minus 1. And n was the sample size. In this case, it's not the sample size. It's not the 100 people that we looked at, but it's the number of categories that we're testing or that we're looking for a distribution. And so in this case, there are 5 categories of 5 different flavors of Lifesaver candy. And so for this, our degree of freedom is going to be 4. So we're going to use the chi-square distribution with 4 degrees of freedom. now you're starting to see how, remember when I said the degrees of freedom we're going to use are going to be much less than 90. We're not going to get close to normal. If we were going to do a goodness of fit test, that would mean we'd have to have at least 91 categories. That doesn't happen all that often. Okay, so first things first, we got to get degree of freedom. Boom. Okay, now here's how we're going to actually calculate our chi-square number. Okay, so this is like, you know how we have a t value, we have a z, right? We have t score, we have z score. Well, this is a chi-square score. Okay, so our chi-square, it's going to equal the sum of this. We're going to take the observed minus the expected and square it. And then we're going to divide that by the expected. And we're going to add this up, the sum, and this just means to add up. We're going to add this up, one for each of the categories. So if we were to look at this specific set, here's how you would calculate that chi-square. We're going to do 32 minus 20 squared over 20. 32 minus 20, O minus E, squared over E. The next one would be 28 minus 20 squared over 20. And then 16 minus 20 squared over 20. 14 minus 20 squared over 20. And 10 minus 20 squared over 20. So if you ask me, well, why do we do this? I'm just going to say, because that's how the goodness of fit works. That's how this is designed. You can kind of see what's going on, though. This is going to be small if the difference between what we expected and observed is small. So the chi-square number, it's going to get bigger if what we're seeing doesn't match what we're expecting. Okay, so smaller chi-square number means it's better. Bigger chi-square number means it doesn't fit as well. All right, well, for this set of data, I think I've got a number here somewhere for that chi-square number. I don't. I think it might be 18. I'm not really sure. We'll use a calculator to figure it out. All right, so then we look at that chi-square number, and we have to compare it against our significance level. How sure are we? All right. Well, I'll tell you what. Let me show you how we can use the calculator to do this. Okay, so I'm going to go ahead and jump straight to that. So give me a second here. I'm going to pull up and share the calculator screen so you can see where we find this and how it works. All right, so here's our calculator. And depending upon what you're doing and how you want to do this, you're going to go to different places. So let's go to stat. We're going to go to stat because that's where we have all our tests. I'm going to arrow over to test. Okay, so we see all the tests that we're used to. If we arrow down, see how there's an arrow on the 9? That tells you that there are actually more that are further down. So we'll arrow down. There's another guy, a couple more. Okay, so I just wanted to get this far to show you the two. So we've got two here. One's called chi-squared test. So you notice how it's a little curvy x squared, so chi-squared test. And the other one is chi-squared goodness of fit. Well, we're going to go ahead and do a goodness of fit test. Let me show you what it's going to ask you. So it's going to ask you a couple things. The first is the observed data. And you notice how it's saying L3, L2. That suggests we want to put this into a list. So we'll go back and we'll do that in a second. But notice it asks for observed data and expected data. So if you look at the whiteboard, the observed numbers are going to be those 32, 28, 16, 14, and 10. And then the expected values, those are going to be all those 20. And then the other thing that you have to tell it is your degree of freedom. All right, so that's why we have to calculate our degree of freedom. So let me back out of this. Yeah, I don't use the TIA for all that often. All right, here we go. Go ahead. Calculate the calculator. So ignore these numbers. These numbers don't mean anything. And in fact, it doesn't even like it. So. All right, so let's go stat and let's put in our list. So we'll edit. So let's put in these numbers. Let me go ahead and clear list 2 here. And let's make list 2 be our observed values. So 32, 28, 16, 14, and 10. All right, so those were the ones that we actually got when we asked 100 people. But what we expected over here is 20 for each of these. So list 2's got my observed, list 3's got my expected. All right, now let's go do the test. So we'll go stat, test. We got to get the goodness of fit. So that's that guy on D. All right, goodness of fit. So let's see, our observed was L2. I put it in, so our first one was the observed. So observed was in L2. Our expected was in L3. And our degrees of freedom were 4. There was 1 less than the number of categories. So, I'm not going to draw it, so I don't really care about the color. So we'll go ahead and hit calculate. So notice that it spits out some things. So the first is the chi-squared value. Oh, my memory was right. That 18 is our chi-square number. All right, so there's our chi-square number. And then it's got a p-value. And this p-value is the same kind of idea as we've had forever. This is the probability that our null hypothesis is correct, or the probability we would get this result if the null hypothesis were correct. Think about what our null hypothesis was. Our null hypothesis was that the flavor choice is uniform. And if the flavor choice is uniform, there's a less than 1/10, or there's around a 0.1% chance that we would get numbers like we got. Okay, so then we get degrees of freedom equals 4. And then that row that says CNTRB, a bunch of numbers, don't worry about that right now. That doesn't really affect us at this point. All right. But the key is that p-value. So I'm going to go ahead and write that on the board. Yeah, p equals 0.001234. Oh, that's kind of fun. 0.001234. All right, so this is how I recommend you do it. Do it as a goodness of fit test. But I want to show you what it looks like if you go to the other test that just said chi-square. So go stat, test, come up here to where it says chi-square test. All right, now I'm going to highly recommend you don't use this one, but instead use the goodness of fit, because now notice where it says observed and expected. So we still want to put in our observed and expected numbers. But you'll see there's like an A that's in brackets. That's asking you to put in a matrix. Now, I don't know what you guys know about matrices. You may not know anything about them. And that's totally fine, which is why I don't want to go into it. But if you want to use this, you have to create matrices, A and B. You do that on the calculator. You can see maybe here that the matrix is blue above the -1 power. So if we were to get there, I really need to learn how to get out of this. Oh, there's quit. Okay, so you want to put in a matrix. You do second matrix. And you notice that it says like names A, B, C, D, and so on. So you would have to edit. So we want to edit matrix A, and then we'd have to put in everything. That's way too complicated. Don't do that. Just do the goodness of it. All right, now where you find yours otherwise, it will depend on your calculator, but at least you can see where to find it on the TI-84. All right, so we get a p-value, which now we can use to interpret just like we always do. So let's think about what our null hypothesis was. So first of all, we had to set an alpha. I didn't set an alpha, but let's just say for the sake of having a number, we went with alpha of 0.05, kind of our standard, right, for 5%. So we would see here that p is less than alpha. So that means that we're going to reject the null hypothesis. So the null hypothesis said, we believe that the choice of favorite flavor, is uniform. And we now have enough evidence, there's statistically significant evidence to say favorite flavor of Lifesaver candy is not uniform. Right, now notice we didn't say cherry is the most favorite, pineapple is least liked. Like we didn't say anything like that. We just said that it's not uniform. It doesn't follow this distribution as we expect. All right, so that's the process of a goodness of fit test. It really is. How do our observed numbers compare to our expected? You can punch it in the black box and get your lovely p-value, which then again will tell you how good does it fit. But the null hypothesis is always, in these cases, the null hypothesis is that the population follows the distribution that we expect. So if we reject the null hypothesis, that's saying that our distribution doesn't appear right. Right? If we fail to reject it, we're saying, well, there's not evidence to say that that distribution isn't right. Not that it is correct, but that there isn't evidence to show that it's not. All right, so let me do one more, and then we'll talk about this exam thingy. All right, so here's another example. Let's say we talk to the US Census Bureau, and we're told the following, that so according to the US Census Bureau, states that 13% of adults never graduate high school. That 30% graduate high school but don't take any college. That 29% have some college experience, and 28% graduate from college. Okay, so you guys would be in the 29% that have some college experience. You've taken some college classes, but you haven't graduated yet. I'm assuming nobody in this group has already gotten a college degree and then is coming back for more math, but we're just gonna go with that. I would be in the 28% that have graduated from college. Right? But we go to all adults in the country and this is what we find. Okay. All right, so here's what we're thinking, what we want to look at. Let's say we're looking at people in El Dorado County. And for those of you who don't know, El Dorado County is the county that South Lake Tahoe is in. All right, so we sample 300 adults in El Dorado County. And this is what we find. So I'm going to call it no high school, some college, and then college grad. Okay, that's what we're going to, I'll label those 4 groups. So we go, we count, and so we have 43 that didn't finish high school, 76 that have their high school diploma but no college, 96 that have taken some college classes, and 85 that have a degree of some type. Okay, so this is what we found. So here's the question. I guess I'm even going to write the null hypothesis. The null hypothesis would be that adults in El Dorado County follow the national distribution. So the alternate hypothesis would be adults in El Dorado do not follow the national distribution. So basically what we're looking at here is El Dorado County, are the people of El Dorado County similar to the rest of the United States? All right, so yes, no, good, bad, good. There's no judgment on this. It's just, are the people in El Dorado County, do they follow a similar distribution? All right, well, that means that these are our observed values, right? 43, 76, 96, and 85. So the question then is, what were the expected values? How many should have actually said they did not graduate from high school? How many of them should be high school graduates and all that, if this distribution is correct? So how do you think we're going to find those numbers. I mean, the other one, the Lifesaver one was easy. Oh, there's 100 of them. We just divide by 5. How do you think we can actually figure out? Let's start with how many of them should not have graduated from high school? What is the expected value for that first number? Can anybody tell me what that is? All right, so Willie, you just put in the chat box 39. How'd you get that number? And I'll even do you a favor. Okay, so you said 300 times 0.13. I was going to tell you, you are correct. And that is exactly it. We know that 13% should have said that they're not high school graduates. So we just need to find 13% of 300. So this is going to be 39, which is the 0.13 times 300. So you could do similar things. The 30% that graduated high school but haven't gone to college, 0.13 times 30. Or I say not 0.3 times 300, which would be 90. 29% have some college, so take 0.29 times 300. That's 87. And then 28% of 300, that's going to be 84. So if it really truly did follow this distribution and we asked 300 people, this is what we should expect. 13% of 300, 30% of 300, 29% of 300, 28%. All right, well, we got our numbers. Let's test them. So pull up the calculator again. All right, so let's get out of this. We're going to go stat. Let's begin by editing our lists. So we'll go ahead and use list 2 and 3 again. But let's change these for our values. So the observed were 43, 76, 96, and 85. So I'll just delete that guy. All right, so let's arrow over, and these were what we expected. So 39, 90, 87, 84. Delete that guy. So there are observed and expected. All right, so now let's go to stat. I'm going to do a test. We're going to do goodness of fit. Okay, for goodness of fit. The observed were L2, our expected were L3. But our degree of freedom is different. What's it now? What's going to go in for our degree of freedom? Because it's not 4. All right, thanks, Willie. It's 3, because remember, it's always 1 less than our categories. So we had 4 categories. So we have to subtract 1. That makes our degree of freedom 3. All right, so arrow down, we'll hit enter, so calculate. All right, so here are our chi-square, or here's our data. So the chi-square number, 3.53. So remember, that's smaller. Last time we saw, what was it, 18. This one's 3.53. That means that our data fits a little bit better. And we actually see that with the p-value as well. Right? So we found a p of 0.3167. Write that down. All right, well, let's talk about what that means. So again, I didn't specify a p. So let's go with the good old, or sorry, an alpha. Let's go with the alpha of 0.05, kind of our standard. All right, so now p is greater than alpha. And since p is greater than alpha, that means we fail to reject H naught. All right, so here's the result now. So we're going to fail to reject H naught. So that means that we don't have enough evidence to say that El Dorado County people are different than the national distribution. Right? We don't have enough information to say that this isn't true. So we're not saying that El Dorado County residents follow the national distribution. We're just saying that we can't say that they don't. There's not information to say that they're different. Right? So at the 5% level, we're going to say, yeah, I can't reject this. I'm not confident to say that El Dorado County adults are different than the national. They could be, right? They could be. I could still be making a mistake, but it's very unlikely now. It's a 30% chance, right? As opposed to 5%. So it's very unlikely that, it's not likely that this is incorrect. Okay, so hopefully you're seeing that at the end of the day, hypothesis test is the same. We look at this p-value and we see how it compares to alpha and go from there. All right, so this is the first thing that you can do with chi-square. It's goodness of fit. The other two we'll look at next week. All right, I want to spend the remaining bit of our time to talk about the exam that's coming up and some other things. Okay, so I'm going to hop down so I can sit down. So I'll be right back with you on the other screen in just 1 second. All right, so next time is our exam, right? We got exam on Thursday. So the first thing I want to let you know is what it's going to cover. All right, it's going to be on chapters 6 through 10. I'll go ahead and put this in the chat box as well. But the exam is going to cover chapters 6 through 10. So what does that mean? All right, in terms of topics and all that. So chapter 6 was all about the normal distribution, right? So it's the chapter 6 was where we started talking about continuous distributions, probability distribution. And so it's going to be the normal distribution. I'm not going to ask about the uniform and other stuff, but it's going to be from normal on. Okay, so you definitely need to know about the normal distribution. You need to know how to find z-scores. You need to know how to interpret z-scores. You need to know how to find, get standard deviation and mean and all that. Don't worry about the formulas, right? Because remember, the formulas for those are pretty gnarly. But know how to use your calculator to get all the information for normal distributions. Okay, so we did normal distributions. Then we talked about the central limit theorem. That was chapter 7. And so the central limit theorem, things we were looking at there, remember there were a couple different forms for that. But it was basically looking at the distribution of the means of samples, right? So central limit theorem was all about, well, what if you take a bunch of different samples and you look at their means, how are their means distributed? And we saw that as you take more and more samples, those sample means get distributed normally. And we also looked at the sum of samples and the means of the sums of samples. And so they were really like the two different forms that we used. And each of them, we got the mean and the standard deviation in a slightly different way. For the samples, for the sample means, the mean was the same as the distribution of the original, and the standard deviation was the standard deviation times the square root of n, or divided by the square root of n. Hopefully you can remember that. You can go back and look at it. And then if we did the sums, the mean was the product of n and the mean, and the standard deviation was the square root of n times the standard deviation. And so we use the central limit theorem to kind of talk about the distribution of sample means. All right, and then in chapter 8, we did confidence intervals. And so confidence intervals are exactly what they sound like. We had to specify a percent confidence level. And then we created an error bound and added and subtracted that to form our intervals. So you could do it with means or with proportions, but remember there are different formulas. There's different ways of getting it. But the interval, confidence intervals, again, let's say we were at a 90% confidence level. That's saying that we're 90% sure that the actual mean or proportion is somewhere in that interval. Or alternatively, if you were to take a sample, 90% of the time, its mean or proportion would be in that interval. Okay, so it's basically just saying, how sure are we? The bigger we make our confidence level, the bigger our interval gets, because we have to catch more possibility. The less variable our data is. If it's got small standard deviation, those confidence levels get smaller, or confidence intervals get smaller. But anyway, so know how to calculate confidence intervals, and also figure out how to find the size of samples that are needed. So think about this last quiz that you guys took. Quite a bit of that was from chapter 8. Okay, so then comes chapter 9 and 10. And 9 and 10, those are hypothesis testing. Chapter 9 was hypothesis testing with 1 sample, and chapter 10 was hypothesis testing with 2 samples. They're similar in the fact that we create the null hypothesis, which is always the equal version, and then the alternate hypothesis is the either greater than, less than, or not equal. We use similar commands on the calculator, but they're different, right? Obviously, there's the 1 prop z versus 2 prop z, things like that. But important things here. Know the difference between when to use z and when to use t, right? We use the z test when we know population standard deviation. If we don't know that, we use t test. That matters because you can get very different p-values out depending upon which you do. So some recommendations for kind of review for hypothesis testing for chapters 9 and 10. Practice reading them. Like literally practice reading them and dissect the important information. Okay, so first and foremost, are we doing means or are we doing proportions? And you may have noticed, like when we did the homework together today, that's the first thing I asked you. It's like, is this a mean or a proportion? Okay, because if it's a proportion, that's easy. There's no choices. You do either one prop Z or two prop Z, depending if you're doing one or two samples. And that should be pretty easy to tell from the wording in the context, right? But it's easy, you don't have to think about it. If you're doing a mean, read through very carefully and see if you're giving a population standard deviation. Now, there are a lot of times we get standard deviations. Think about that one on the quiz that you guys just took, where we did the hypothesis test. That one, there was a standard deviation given, but it was the standard deviation of the sample. In that case, got to use T. Okay, so if you're doing means, now look, do we have population standard deviation or not? Yes, use a Z. No, use a T. Okay, and then the same thing with two samples. If you've got your two samples, you need to know population standard deviations for both. That's really rare. So almost always when you're doing two samples, it's going to be a T-test. Almost always. Okay. But there are situations where you are given both, right? And I've showed you examples in both cases. All right, so that's the content. That's what's going to be on it. In terms of what the problems are going to look like, they're going to be very similar to what have been on quizzes and what's been on the homework. I will tell you that I'm not going to, like, I might ask you to write in, have you write in words the result of the hypothesis test. But I'm not going to give you, like how they like to give you 3 or 4 different things and you have to pick which of those is actually saying. I'm not going to do that to you. Okay. But some things I'm definitely going to look for. I want to see you say reject or fail to reject the null hypothesis. Don't ever say, that whatever the null hypothesis statement is, don't ever say that's true or that I accept it. Don't do that, because that's not what you're doing. You can say it's not true. There's evidence to say it's not true, but you can't say there's evidence to suggest that it's correct. You can say that there's not enough evidence to claim that it's false. That's your fail to reject. Okay, so just watch the wording on that. But I will expect you to write out at least, in the context of the problem, what does this mean, right? What at the end of the day, what does this study have to say? So go back and look at quizzes, look at the homeworks. It's going to be very similar. Practice with your calculator or whatever form of technology you're using. Practice with that so that you have that down, so you don't have to think about that come exam time. Right? You want to just be able to go, oh, I'm doing a T-test. Okay, go to T-test, and you know exactly what you're going to be typing in, so you've already got it. Practice doing that. The more comfortable you are with your technology, the easier the exam is going to be. Okay, so because we have an exam, we don't have class, right? We're not going to have class. We're going to start at the normal time. So the exam will be available starting at 3:30, and it's going to be due uploaded by 6. Please don't push it. You guys don't understand how much more difficult it is for me to deal with stuff when it gets emailed or put in as a message and all that. Please, please, please upload it. Okay. It should not take you 2.5 hours to do this test by any means. I think at most it's going to take you 1.5 hours to actually do it. So you'll have plenty of time to get it uploaded. Please, 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 please get it uploaded. All right. Okay, other than that, I will be around for office hours tomorrow, like usual, and I'm accessible via email and all that if questions come up. Obviously, you don't want to wait till the last minute for your questions because I do have other things that are going on that I may not be able to get to it right away. So, but please don't hesitate to reach out if you've got questions, all right? So I think with that, I'm done. Any questions you guys have before we wrap it up? All right, well, hearing none and seeing none, then I will wish you all a wonderful couple of days.